Welcome everybody to today's webinar on wall design in RISA. I'm Matt Brown, and today we're going to be talking about walls within the program, and we're just going to be taking a look at RISA 3D today, since that's where most of the wall design is actually done. And the version for that one I'll be using is the latest version, which is 11.0.2. Now, I know we've done a number of wall webinars in the past that have usually been very material specific. So we've talked about wood wall, masonry, or concrete walls, and topics that are very specific to those material types. But today I'd like to do a more general wall topic, and in this one we'll talk about some of the analysis aspects of walls that you may not be familiar with in the program, and we'll really be able to get into the nitty-gritty of that. So today what we're going to talk about, as you can see here, I'm going to show you a comparison of how walls and plates compare against each other and why you would use walls as opposed to plates. What are your big advantages there? We'll take a look at a lot of aspects relating to wall-specific things, boundary conditions, openings. We're going to look at how these all affect the analysis of forces and stresses within the wall, and we'll take a look at that. And then, of course, how walls interact between each other and other members and the such. We will dive into some of the material-specific features and talk about some uniqueness between masonry versus concrete versus wood. And wall stiffness is another big topic. So you can see we've got a number of different topics here, and I'm going to build some models just live here. So rather than you having to sit through some PowerPoint slides, you'll be able to see live in the program how this all works. So to begin with, I am going to open up RISA 3D, and we are going to build a model where we're going to compare some plates against some walls. And so in order to do that, I'm going to come in and edit my drawing grid to make it a little bit larger so that I can draw things in. And we're going to come in here, and I'm going to draw, using plates, a general concrete wall. Now keep in mind that plates are general material types, which means that even though we call this general concrete, it's not actual concrete. We're not going to get the behavior of concrete. All this has is just the properties of concrete in terms of the modulus of elasticity, your shear modulus, and your density. So you'll note here that when we define general concrete for NW, there's no F prime C. So we have no concrete strength listed in here. Whereas under concrete, in this tab, here we have Conc 4000 NW, where we do have design properties, F prime C, and then your rebar strengths. So that tells you right there that when we use this Gen Conc 4 NW, this is just for analysis. This isn't going to give us any code checking or design. The program knows nothing about the actual capacity of this material, but it can give us accurate forces and stresses within it. So I'm going to come back here to draw new plates, and we're going to pick out that Gen Conc 4 NW, and I'm going to give this a 6-inch thickness. And what we're going to do is we're going to draw an 18-foot long wall. So I'm going to come in here and just click to draw one gigantic plate. Now, those of you who have attended my plates webinar will know that, of course, one huge plate is not going to give accurate results in this case. So what we need to do is we need to submesh this. And in this case, I'm going to go in and modify submesh quads, and we're going to submesh this 18 by 10, which means we're going to get plates roughly 12 inches by 12 inches. With a mesh like this on this wall, we should get really good, accurate results in this case. Now, in order to compare the plates against the walls, what I'm also going to do is I'm going to draw a wall right next to this. And so when I go in to draw walls, you'll see here that I can choose under my material for walls, masonry, wood, or concrete. Now note that when I choose concrete, I have the actual concrete materials as opposed to when I choose general, where it's the general concrete materials. So that tells me that concrete is going to give me a design, whereas general will really only give me an analysis. And for the case of this, we're really just concerned about analysis at this point, so I'm going to stick with a general wall. So I'm going to choose general concrete. And I'm going to come in here and I'm going to draw a similar wall here where we are going to make it also 18 feet long. And there we go. So now we have the general wall shown. And the next thing I need to do is I need to apply some loads to the plates and the wall, of course. So I'm going to come in here and set up two basic load cases in this case. I'm going to set up a dead load and a seismic load. And so for the categories, for dead load, we'll just put DL, EL for the seismic, and I'll be sure to turn on the Y gravity so we get the self-weight of the wall included. And then I'm going to come in here and load these two walls. Now, you may notice in this case that what we've got here is plates where I can't put distributed loads on the top. So I'll show you in walls, I can come in here and I can apply a -1 kip per foot gravity load under dead load, and I can just click on the wall edge and apply that. And you see how convenient that is. Now, if I want to do something similar in the plates, what I actually have to do is come in here and I have to put in individual loads of -1 kips, and I know my plates are 1 foot apart. So here, I've got to drop those in at each plate corner. And then, of course, at the ends, that node right there only has half the tributary area, so I need to do a -0.5. So right here already, you can see a big advantage of going with walls versus plates in that my loading is much simpler. Now, I want to do the same thing for the earthquake load, so I'm going to come back in and do a distributed load in the global X direction, and I'll set that up under seismic here. Similarly, with wall panels, I can just click on the edge. It's going to load up that wall, whereas with the plates, I need to come in and I need to apply this as individual loads to the individual nodes. So there's 1 kip at each node there, and we're going to put in 0.5 at each end. Now, this is more accurate than just lumping one giant load right at the corner of the wall. If we were to do that, then what we would get is huge stress concentrations right here at the corner, where really we want to drag this load into the wall all the way across. Now, at this point, I'm going to come in and put in some boundary conditions at the bottom of the plates here. And so I have individual pin boundary conditions at each plate. And then for the wall, I can actually just leave the bottom of the wall blank, and what will happen is when we solve, if there's no boundary condition below the wall, it'll automatically place a continuous pinned boundary condition at the bottom of that. So I'll come into the load combinations. We will say total load, and I will use the appropriate load factors here for ASD. So we'll use dead load with a factor of 1, and earthquake load with a factor of 0.7. And then I will solve the model. And what we can do now is we can take a look at the reactions between these. So if I take a look in the joint reactions spreadsheet here, what I can see is I've got a total reaction in my entire model of 25.2 kips. So that's the total downward force. And for the plates, what I'm going to get is a reaction at each node along here. But if we sum up all of those, in the case of the wall panel, we end up with 12.6 kips. And so that's equal to the plates right here. So we can see basically the wall should account for about half of what the plates are in this case. Let me just come in here and check something. I noticed when I was in here that we were off in terms of for the Y direction, the wall doesn't add up to half of what the plates are, and so that tells me right there my thickness is wrong. I wanted to do a 6-inch wall. So a little bit of checking of things like these joint reactions is really good in order for you to be able to identify maybe errors that you've made in your model, because, of course, the principle always applies, garbage in, garbage out. So now here we can also compare these reactions graphically. I can come in and turn on these reactions, and we can see exactly what's happening at the base of the wall there. I'll shut off the display of loads to make this easier. So here you can actually see there's a little bit of uplift at this end and, of course, a downward spiking load over on this end due to that lateral force. You can see the numbers match up perfectly. And the reason for that is even though this wall looks like one giant element, I can actually come in and turn on this mesh display, which shows me that behind the scenes, the program has actually meshed this wall for me, and so it's doing an analysis just like it would with the plates, except for I don't have to actually submesh it. I don't have to have all these nodes and these individual plate results. I just get one big wall result, which is going to match what my plates were anyhow. Now we can also compare the stresses and forces in this case. So I can come in here and turn on the display of plate stresses. And let's just see here, if I compare the walls against the plates, let me add in a plate stress button and a plate force button here. So now I can compare, this is the Fx, and the Fx is the axial in-plane wall force. And we'll see that everything matches up perfectly between these. And similarly with the Fy, you're going to get very similar results between the plates and the walls. And that's, of course, because we are checking these for all of the above. So here we can see with every result that I've gotten here, basically, it's matching up side by side. So without having to do all the submeshing, I was able to pull this off. Now, of course, the submeshing in this case was really just one step, but why is that a big advantage? Well, I'll show you on here. What I'm going to do is I'm going to add an opening into the wall. And so in order to do that, what I want is I want a door opening that's 2.5 feet in from the left side of this wall. And I'm going to need to go in and split these plates in order to do that. So I'm going to do a 2x1 quad submesh because these plates are 1 foot by 1 foot. So I need to split the plates as shown here in order to get that. And this will give me the ability to add in this opening. And of course I add the opening by coming in and deleting the plates that are where the opening would be. So it's a little bit of work in this case to come in here and add this opening in. I've got to take care of clean up on all these excess nodes that I've got laying around. I've got to come in and add in new boundary conditions at these new nodes that I've created. And of course from the plates webinar we know that it's very bad to have a node on a plate that falls on the edge of another plate because those won't be connected to each other. So in order to get connectivity on this wall, I actually need to come in here and I need to delete some of these existing plates and then redraw them in. So I need to come in here and draw in these 6-inch plates. According to this, I'm going to do some trapezoidal plates so that we end up with all plate corners touching other plate corners and it's a good mesh. So that's how I would do that opening in the plate model. In the wall model, it's far easier. If I double-click on the wall, this is going to pull up my wall panel editor. I have a giant region on the wall, and we'll explain regions in a minute. For now, I'm going to delete that region, and I can come down here under my grid increments, and I can control what my drawing grid is on the wall, and it's as easy as coming in here and saying draw opening. And so when I do that now, here I've got an opening drawn in the wall. And we'll see that even with that opening drawn, the results should still be fairly familiar. So I'm going to come in here and solve. And I got an instability. That's actually an out-of-plane instability in this case. I forgot to restrain the wall in the Z direction. And so what we can see here now is the results are still very similar to each other, but they are off ever so slightly. And the reason why they're off slightly is the mesh is a little bit different on the wall than it is in the plates. Here I've got 3 plates across, whereas the wall mesher managed to do this in just 2 plates because it was able to adapt and move all of these nodes on the fly. But even so, even though there's slight differences between the two of them here, the overall results should be still fairly similar. If I take a look at the forces in the local X direction, this would be in the lateral direction. We can see they're all very similar here, and of course if I flip it over to Fy, everything matches up pretty closely. So you can see it's very easy to work with that within the walls. Now, of course, the contours are only going to give us relative rough numbers to see in this case. These are really ballpark figures. They're not exact numbers. So if I want to get exact numbers, what I need to do is I need to use the internal force summation tool. And for that, I'm going to select just a portion of this wall pier right here, and use the internal force summation tool. That's this one down here, the sigma with the arrow. And with this, I can get a cut. Now, in this cut, what we're going to see is that the F1, which is reported right down at the bottom of the screen here, this is the shear in the wall. The F2 is going to be the vertical axial force in this pier of the wall. And the M3 is going to be the moment. And so scrolling through here, I can see a constant shear of about 464 pounds. And going up and down, my axial force, of course, increases. And so what we see here is the axial force tops out at about 3.6 kips and the moment at about 2.6 kips. Now, if I take this wall here and I open it up, what we're going to see is that it's created a region, R3, just to the left of the door that matches up that area we were looking at. And what the program will do is take all the forces and stresses that it got from the FEA analysis that's in that region right there, and it will report them to us in a very user-friendly manner. So if I pull up a detail report for the wall and take a look at that region, R3, what I get here is an axial force diagram, a shear force diagram, and a moment diagram. And so in this case, what we can see is that our shear force shown down near the bottom is 487 pounds as opposed to, I believe it was 484 from the plate model. Our plate moment on there was about 2.6 kip feet. This is 2.7, and that was about 3.6 kips of axial, and it's about 3.6 kips of axial here. So you can see the results match up almost perfectly, except for rather than needing to pull out that internal force summation tool, here I've actually got a detail report that shows me all the wall forces that I can print out. So you can see that it's much better reporting for walls to do it that way as opposed to using plates. So that's the first part of this, is I just wanted to explain the difference and similarities between walls and plates and how they can be used interchangeably. But if you have an application where it's a vertical element that's rectangular in shape, what we'd call a wall, then I would much prefer to use the wall panel as opposed to meshing the whole thing out of plates, which can be a lot of work. Now next, I'd like to talk about how those wall forces are presented. So I'm going to open up a new model to show you something here. So in this new model, I'm going to create two wall panels, and I'm going to do these as general concrete once again, 6 inches thick. And I'm going to draw two 10-foot by 10-foot wall panels. And we're going to set different boundary conditions on them to see how these differ. So there's one, and here is the other one. And when I double-click on a wall panel, what that does is that pulls open the wall panel editor. And in the wall panel editor, I can apply boundary conditions. And in here, when I apply a boundary condition, I can set a continuous boundary condition along a given edge. So on this wall here, I'm going to put a continuous pin boundary condition along the bottom. And at the top of it, I want a continuous boundary condition only in the Z direction. That's out of plane. And so that makes this wall effectively simply supported. So now if I come out here and snap into an isometric view, you'll see that wall is pinned along the bottom and simply supported on the top. Now I'm going to take this identical wall just next to it, and I'm going to put in the same simply supported boundary conditions, but I'm going to put them on the sides of the wall rather than on the top of the wall. And so what we'll see here when I click on the side of that is now this wall is continuously supported along that edge and this edge as opposed to this edge and this edge. And then I'm going to come in and I'm going to apply a surface load in the global Z direction of 100 pounds a square foot. And we're going to compare the difference in forces between these two different walls. So I'll come in and solve that load combination. And what you're going to find out is when we report to you the forces in the wall for out of plane, what we're taking a look at is we're taking a look at bending about the horizontal axis. That is bending that's occurring in the vertical direction. So all of our out-of-plane force results are assuming that the wall spans vertically, not horizontally. And this is a very important thing to consider. So in this case, here on this wall, if I come in and take a look at the detail report out of plane, we see a maximum moment of 12.375 kip feet. And so we can see that perfect bending out of plane. And keep in mind that this diagram is shown as bending about the vertical axis. Now in this wall here, of course, we know that that wall is going to span horizontally, and I can even see, if I turn on the deflected shape here, that we should see it bending outwards this way as opposed to this wall, which is bending this way. This wall is bending about the horizontal axis. This wall is bending about the vertical axis. Now, taking a look at the forces, of course, we're still getting forces reported, for these walls. But here I've got the bending about the horizontal axis and bending about the vertical axis. So the forces and stresses are still present in this wall. But if I go to the detail report, you're going to see very little moment, only about 1 kip feet as opposed to the 12 kip feet. And that's just due to some warping that occurs right in the middle of the wall here. So keep in mind that even though those forces are present, the program's not reporting them to you. And so when you get a report for out-of-plane forces, what you're looking at here in the case of a wall that's spanning horizontally as opposed to spanning vertically is a underreported moment, I suppose you could say. Now, it's not actually underreported. This is the moment about the vertical axis. It's just that we don't tell you directly what the moment is about the horizontal axis. So for that, I would have to come in here and take a look at something like the wall contours to see here how much moment that we've got going on. In this case, it's reporting at about 1.3 kip feet per foot. And of course, if I multiply that by the 10 foot of wall height, that would be about 13 kip feet, which is very comparable to the 12.4 that we get reported out of here. So very similar in that regard. But it is something very important to consider. So let's take a look at this within the context of a more realistic model as opposed to just a very basic case here where I've got these continuous boundary conditions. So I'm going to come in here and create a new model where we are going to do an elevator shaft. And so for that, I'm going to create, once again, general concrete walls. We're going to do these as 6 inches thick. And I'm going to create a wall that is 12 feet high and 24 feet long. And with this wall, I'm going to double-click on it to open the wall panel editor, and I'm going to put in some openings. To do that, I just go to this bottom left corner here, and I can enter in the dimensions for how I want the openings. So I'm going to say 3, 6, 6, 6, 3, and in the vertical direction, I'm just going to say 8. And what that gives me is these snap points, 3, 6, 6, 6, 3, that allows me to draw these 2 6-foot wide openings for the elevator doors with the appropriate distance away from the edge of the wall. So once again, a lot easier than doing plates in that case. So with this wall in place, I'll snap into an isometric view, and I want to copy this wall over, so I can just use the copy offset command here to copy that forward about 6 feet in this case. And I'm going to take this second new wall that's been created, and I'm going to get rid of those openings. So I can do that by double-clicking on the wall, and in the wall panel editor, just deleting these openings. So here now I've got one wall sitting in front of the other one. And then I'm going to draw in the end walls here with no openings in them. So I will just drop those in on each end. And here we've got this box, which represents our shaft. So with one floor drawn, now I can actually just copy this upward. So I'm going to use the copy command to copy it up 2 levels. And here we can see we now have a 3-story elevator shaft. And I want to assume that there's flooring all the way around this shaft that's providing a diaphragm bracing at each floor. So I'm going to come in and define diaphragms, rigid, at each floor level, and that's just going to stabilize this entire structure so that we can look at it a little more clearly with respect to just the wall results. And so you can see what I've done here is I've placed diaphragms at each floor level. So that'll tie everything together well. Next, I'll come into the basic load cases, and we will set up a dead, a wind X, and a wind Z basic load case. For the dead, of course, that's the DL category. Wind in the X direction I'll set as WLX, and I'll set wind in the Z direction as WLZ. And for the dead load here, I'm just going to put in a gravity of -1, and that'll just account for the self-weight. And then I'll come in and I will apply wind loads to this structure, and we'll just assume that the wind is acting only on one face of the structure. So for that, I can come into the wall panel surface loads here, and I can set the X direction for the X direction wind load, and we will put that at, let's say, 20 pounds a square foot, so 0.02 KSF. And I want to drop that on this side of the structure. And so for that, it can be a little bit difficult sometimes. If I have these walls all together, I might need to rotate around a little bit in order to accomplish what I'm trying to do. But if I get this model rotated correctly, I should be able to reach a point where I can peer through it and click on the wall that I want to get this on. And so there we go. Now I've got 20 PSF on that side of the structure. And that was kind of tough to get to. As you saw, I had to click a few times. I'm going to show you a trick for how I can apply that wind load on the other side and make it easier. What I'm actually going to do is I'm going to come in here and I'm going to put in a plan view and select only a few of these walls here. So now with just these walls selected and the other walls unselected, it should be fairly easy for me to come in and add that Z direction wind load, which I'll come in here and add that. Now that load will only apply to the selected walls, so the grayed out ones don't get in the way and I don't accidentally click on those. So that's just a handy trick to be able to put into the model. So let's see now how this compares in terms of the loads in each direction. And you know what, I'm actually going to come in here and we're going to put in loads on both sides, just to make sure that we're really getting an apples-to-apples comparison in this case. So I've got wind direction on both sides of that shaft, and we're also going to come in and go back and put in that X direction wind load as well. Let's just see. So we've got it applied on that side. Here I want to put in that 20 PSF X direction wind load on these walls. And so this will allow us to compare against a short span direction versus a long span direction. Essentially what I've got going on here is if I isolate the middle floor of this structure, let me just lock everything else out for a moment, I've got out-of-plane loads on the wall going in this direction and this direction. Now with the diaphragm above and below, what my goal here was to do is create a situation similar to the previous model that we worked on, where I had one wall that was spanning vertically and another wall that was spanning horizontally. Now in this case, the long wall here, it's going to tend to span vertically due to an out-of-plane load. What we would expect is that any load will generally head up and down to the nearest diaphragm level. Now with these short walls here, it's a much shorter distance to the walls that intersect on either end, and so I would expect that an out-of-plane load on this wall is actually going to span horizontally, that it's going to go into these adjacent walls more likely than it is to go up and down in that case. And so we can actually compare that. If I come in here and take a look at my wall contours, I'm going to come in here and turn on the MY force contour. Oh, I suppose I have to solve the model first. Let's come in here and set up a wind X load combination, DL with a factor of 1, and we will use the ASCE 710 load factors for this one, where I have a 0.7 factor on the wind load. So I'm going to solve that first combination for wind in the X direction. And what you're going to see here is that our X direction moment in this case, or our moment about the horizontal axis for the short end of the wall, because we're looking at WLX, so this is going to be an out-of-plane load on these end walls here, which you can see. You can see my moment is approximately 17 foot-pounds per foot in bending about the horizontal axis. Now, if I flip over to bending about the vertical axis, the MX, now this is bending, I can show this graphically here, maybe if I just exaggerate the deflected shape a little bit. So this is bending outwards, bending about the vertical axis. We can see about 33 foot-pounds per foot. As you can see, it's about double, actually. We're getting much more bending about the vertical axis than the horizontal axis. We can see this wall is spanning horizontally. And in this case, if I were to come in and design for the out-of-plane moment on this wall right here, just taking a look at the detail report in this case, the moment that I'm going to get, that 0.345, is really just going to be for the vertical rebar for this wall. And so if we're talking about this being a concrete wall, the horizontal rebar, which is there to support bending about the vertical axis, in this case needs to be designed for this larger 33 foot-pounds per foot moment, but that's not being accounted for in this case. So it's something that I just wanted to make very clear to you about how the program operates and how your results are being presented, that we do this out-of-plane design for the vertical bending as opposed to the horizontal bending. Now coming in here and solving for wind load in the z direction, what you're going to see is if I compare my my here, this is my bending about the horizontal axis, we can see we've got about 300 kip feet per foot, or foot-pounds per foot. And if I take a look at about the vertical axis, it's much less. It's only about 110. And that's actually occurring right here over these elevator doors. So, of course, taking a look at forces in the z direction, where this wall would primarily span vertically, that's really being covered for the most part in this out-of-plane detail report. We're getting a very realistic number reported to us in this case. So that sort of covers that aspect of the vertical versus horizontally spanning walls. The next thing I'd like to talk about is how area loads get attributed to walls. This is something that you may deal with. So I'm going to come in here on the top of this structure, and I'm going to apply an additional dead load of negative 100 pounds a square foot to the top of this structure using an area load. And so when I apply that load on the top of the wall there, we can actually see how this attributes itself to these walls up at the top. So I'm going to unselect these lower levels and shut off this diaphragm display just so we can see a little more clearly what's going on. And I'm going to go back and solve the model again. And let's just take a look at the transient area loads. The transient area loads show us how a distributed load attributes itself. And what you can see here is, given that I did a two-way load distribution for this area load right here, it's going to just attribute itself to the wall panel edges. This is a really neat feature because it allows us to account for decking that's over the roof of this elevator shaft or the beams without actually having to model those beams or that decking on here. And so you can see what you get with the two-way load distribution is a relatively uniform distribution along these ends. And then over here at the end walls, we just get a little bit of load picked up at each end. And of course, I could come back and do this as a one-way load if I wanted, and then it would just all attribute itself only to walls on one direction and none in walls on the other direction. Let's see how these walls interact with members. I'm going to come in here and copy over some of these nodes in this case. I'll take these two nodes that I've got selected and copy these 5 times at 4 feet on center in the global X direction. And so what we end up with now is snap points to draw in beams. And let's say that for the roof of this elevator shaft, I've got wood 2x8 members, Doug fir, that are going to be spanning across the top here, supporting some sort of a decking. And so in this case, now I've got those set up. I can solve the model again. Now, all I had to do was draw these members where their nodes landed on the edge of the wall. And what happened is it automatically connected those members with these wall panels. So that's pretty convenient. Now, I'm going to switch that area load over a little bit so that we can see how it behaves if it's a one-way direction area load. And so we will come in here and I will put that over to be a one-way load. I'll turn on the display of it, and we'll go to the basic load cases spreadsheet and find that area load and set its distribution to be BC. And now that load is spanning perpendicularly to these members. So coming back, I can take a look at these transient loads, and you'll see that it comes up with an even load on each one of those members there. Now, these beams are actually connecting into the wall, and we can actually see how they're influenced in the wall by taking a look at the wall stresses. And if I come in here and take a look at the Fy, that's the vertical axial stress in the wall, what you'll see here is any time where a beam hits the wall, we get a spike of axial stress that eventually ends up bleeding out everywhere. And this is really that notion of arching action that you see studied primarily over openings and the such, where we see that this initial axial stress bleeds itself out to the point where whatever this elevation is on the wall, about a third of the way down, these individual point loads from the beam reactions have actually come out to be essentially a uniform load in terms of how the wall behaves. And this is all FEA that's handled, so it's fairly easy to model even complex situations and get an accurate result. Now, the next thing that I'm going to do is I am going to move these beams downward, and so we're going to move them all down about 2 feet, and then copy in these nodes that are up at the top. I'm going to copy those down 2 feet as well. And so now what we end up with is these beams being offset downward. I'm going to get rid of the original area load that we had here. And what we have now is basically a parapet type situation where these beams and that roof decking are all set down by some distance. And let's see how that's affected within the model here. So I'm going to solve the model, and we'll take a look at that transient loading, and I'll shut off the display of wall contours. Now what you're going to see here is that these exterior beams end up picking up a decent amount of load, but no load ends up on the wall out here. So this is basically assuming that that decking that runs perpendicular to these beams is not supported over at the wall here, because we will only attribute that area load to a wall panel edge, and there's not an edge here. This is an interior. If I want these walls to pick up their share of the load as opposed to these outside 2x8s picking up a bunch of extra tributary area, what I can do is I can come in and draw what I would call, in this case, basically a ledger beam, or you could also just call it a dummy beam, where I've drawn this beam embedded in the wall, basically. And so with that beam being embedded in the wall, what's going to happen is when I solve, it's now going to pick up that beam for load attribution, and you'll see that that beam ends up loaded right there. Now, you'll also note in this case that I've got differing values for the area load in these beams which have an equal spacing. Whenever you see that, that's a good sign that you might want to reduce your area load mesh size. That's in the global parameters, and that will give you a more accurate distribution of loads. So here you can see more accurately, it should be about 400 pounds a foot on these beams and 200 on these ledger beams. So now, if I take a look at the design of an individual interior beam, of course what we're going to see is that it's simply supported, and so we get a bending moment of about 1.8 kip feet across there. But if I take a look at the design of the ledger beam, here we can look at the moment diagram, and you see it's very small moments, and it's spiking every foot or so. And what that's showing you is that this beam is being meshed into the wall, so it's continuously supported about every foot on center. Coming in here and taking a look at the wall panel mesh, here we can see everywhere one of those nodes falls, that beam is connected at that point. So that's how you would handle getting this load attribution in this parapet type situation where there's no wall edge, is you would just come in and draw in these ledger beams. And the actual design of the beams will be largely irrelevant because, of course, they're continuously supported, or roughly so, by the walls. Now, another thing to consider when you're talking about how do walls and members interact with each other is we need to consider the fact of column and how columns are impacted. So I'm going to come in here and draw a steel column. I'm going to pick out a W10 by 33 column in this case, and we will put this in as a fixed column made out of AE992 steel and rotated 90 degrees. And what you'll see here is I'm going to draw this column being supported at the end of the beam there. And I'm just going to solve this model again. And let's just see how this looks. So what you can see here, when I render it, maybe I can just snap into an elevation view here, is I've got this steel column now embedded in this concrete wall. Now what's going to happen is when I embed this column in the wall and I solve, this is going to fully mesh itself into that wall. And so as a result, I'm going to expect to see on this column that I've got a somewhat jaggedy axial force diagram. And what we're also going to see in this case is that the force in the wall doesn't exactly match what was at the beam. So here I've got this beam with a reaction of about 1.2 kips at the end of it. And if I take a look at the column here, what I'm looking at is about 730 pounds. So where did that other 500 pounds go in this case? Well, what happened was, because the column is fully meshed into the wall, it shares its load with the wall. And so the program is going to take a look at what is the axial stiffness of the wall in this location and what is the axial stiffness of the column here. It's going to consider them to act fully compositely, and so the amount of load distribution to the column versus the wall will just be a ratio of their axial stiffnesses. And so in that case, because we went from about 1.2 kips down to about 0.7 kips, we can see that the wall in this case, is maybe about 40% less stiff than the column, but it is going to pick up that, say, 40% of the load in that case. So if we didn't want this column to act compositely with the wall, what we would have to do is move it out of plane by some small distance. And as long as the column doesn't fall within the plane of the wall, then it can pick up that member's end reaction, and the column will carry the entire reaction of the member. And that's how you would usually treat something like a pilaster or a steel column that's set just inside of a concrete or a masonry wall. So keep that in mind, that if you draw the column embedded in the wall, that it will be sharing quite a bit of its vertical load with the wall, whether you want it to or not. Now, the next thing we're going to do is take a look at some of the material-specific aspects of the program. So for that, I'm going to create a new model. And in this new model, I'm going to create an actual concrete wall. So far, we've been dealing with just general walls. And so for this, we'll come in and put in an 8-inch thick, 4,000 psi concrete wall. And I'm going to draw this as about 12 feet high. Drag that data entry toolbar out of the way. And about 16 feet long. And drop it in like this. And then I'm going to put in a door opening in this wall as well. So in the wall panel editor here, I can set up my opening snap points so that I can have a 4-foot wide door opening right in the middle of the wall here. Now you'll note that it automatically creates a lintel above the opening when I have a concrete wall here. So with that in place, I can snap into an isometric view and copy this wall in the Z direction. And I'm going to create a couple of copies on this one. We'll do 2 at 16 feet. And so here I've got 3 copies of an identical wall. On one end, or in the middle wall here, I'm going to get rid of that opening that we created. And on one of the ends here, rather than doing this as a door opening, I would like a comparable window opening. So I'm going to set up snap points accordingly. Now, you can't modify openings in the program in terms of once you've drawn them, their geometry has to be what they are, but you can delete and redraw, and so that's what I've done in this case. So here I've got 3 different walls that are all similar to each other. I'm going to draw in some perpendicular walls as well just to round out this model so that we can get an entire structure. So I'm going to run some solid 8-inch walls across here. Now, because these 2 walls intersect each other, they're going to fully mesh with each other and fully merge in with each other. And what that means is the program is going to treat this as though this is a monolithically cast concrete wall. Now, that would be different from, say, a precast situation where maybe I wouldn't want that. And if I didn't want this wall to mesh and merge in with the wall running in the other direction, I'd want to make sure to leave a small gap between the 2 walls so that they didn't actually touch each other. Because if they don't actually touch each other, then they're not going to mesh with each other. Now, I will put in a diaphragm in this structure just to stabilize it. And so you can see the diaphragm that I put in there at that roof level. I'm going to come in and set up a couple of basic load cases here for dead and for seismic. And for dead, of course, I'll come in and put in the self-weight. And for seismic, I'm going to put an EL category on that one. For the dead load, we're going to do an area load, and that'll save us the trouble of having the model framing on this structure. And so I will put in the area load across the top of the structure there. And then for seismic load, what I'm going to do, because I have a rigid diaphragm, I can actually model a seismic load as just a single point load, and I don't have to worry about the individual force concentrations and stresses occurring throughout these walls, because this rigid diaphragm is going to attribute this lateral load to the walls running in that direction according to the wall's relative stiffnesses. And this relative stiffness is very important to consider because, of course, we're going to have a different stiffness of this solid wall versus those end walls in this case. And so here, if I solve the model for a total load, and we will do, because this is concrete, dead load with a factor of 1.2, and it's LRFD level, so the seismic load has a factor of 1. What we're going to see here, I'll turn on the labels, wall panels 1, 2, and 3, is that our force distribution in the x direction for 1, 2, and 3 is according to the stiffness of these walls. And what you can see is wall panel 1 picks up 202 kips, significantly less than wall panel 2 at 376 kips. And if you were to divide these two, that would be equal to actually the lateral stiffness of these walls. And then similarly, wall panel 3 picks up 222 kips, so you can see that wall panel 3 with this window opening is a little bit stiffer laterally than wall panel 1, but of course they're far below what the stiffness of wall panel 2 is in that case. And so this is just to point out how the program, because you're modeling these walls as plate elements underneath it, actually is using all of the correct stiffnesses in order to do force distribution in your model. That makes these walls very powerful because you can get a true distribution throughout your structure of your lateral force as opposed to using hand calc estimation methods. So walls are very powerful in that regard. Next, I'm going to take a look in the Wall Design Rules spreadsheet. Now, this may be an area where you haven't been before, but under the Data Entry toolbar, we have a Wall Design Rules spreadsheet where I can set up individual aspects of how a wall is to be designed. Now, in this case, I'm going to rename the initial design rule to be exterior, and I'm going to create a new rule called interior. And you can see there's different tabs for each material. Now, because we're dealing with concrete walls, I want to go to the concrete tab. So I'll go to the concrete wall rebar tab, and here I can set up how the rebar is going to be optimized for this wall. So here I can say for my exterior walls, I want you to use number 6 bars at a maximum spacing of 18 for the vertical. I want you to use number 4 bars at a maximum spacing of 18 for the horizontal. Now, for the interior wall, maybe I want to beef this up a little bit since I know that interior wall is going to be taking a little more force. So I'm going to set this up to use number 8 bars at a maximum of 12 inches spacing. And so you can create as many design rules as you like in order to narrow down what the design of each wall will be. And if I come into the wall panel spreadsheet, I can come in here and set the design rule for any given wall for it to be interior versus exterior. And so now I've set just that middle wall on the interior. And if I solve the model now, we'll actually go back and take a look at those results. And so pulling up a detail report for the wall, what you get in a detail report is you can choose between looking at the overall wall or an individual region. Here for that middle wall, when I choose overall wall, we can see I get a report here summarizing everything about the design of this. The important thing I want to see here is the UC shear. So this is the shear unity check for this, and it's acting as a shear wall. And it's at 0.976, which means that it's about 97% of capacity in that regard. And here we can see the reinforcement results shown, number 8 at 12 on center each face for vertical, and for horizontal, number 4 at 14 inches on center. Now, graphically, I can also double-click on the wall to get this graphic shown if I want to see more clearly what the reinforcement that's required is. Or if I want this in a tabular format, under the Results toolbar, I can pull open this concrete reinforcing spreadsheet where we can get all the results shown right here. Now, how did the program come up with this design? How does it know that's going to work? Well, for that, we need to take a look at each region of the wall. And so if I come into the region here, what we'll see is here's a code check according to the 2011 ACI code. And the program's actually come up with an interaction diagram for the concrete wall. And so it's taking a look at both its axial and bending capacity, and it's able to plot that out and give us a full detailing of the wall shown down here. Of course, for a wall with an opening in it, now there's going to be multiple regions. And region R2 is really along for the ride for the most part. It's not doing too much, but R1 and R3, the full height ones, that's doing most of the heavy lifting for the wall. And so you'll see here that you're going to get different reinforcing results for each one depending on what's required. And I can also double click on here. So here we can see number 6 at 18 on center for this region, number 6 at 14 on center for that region here. So I guess the forces were a little bit different between them, or it may have had something to do with just a minimum area of steel for the size involved. So there's a lot of different aspects that go into this. It gets a little bit complex, to say the least. Coming in here for the opening, we basically get a report for what the lintel above the opening would need to be. Now, at the moment, we don't currently do lintel design for concrete, but we do at least give you the axial, shear, and moment that's occurring in that space that would be the lintel, so that you can go in and do a design for that. Now, I'm going to switch these walls over to be masonry in this case, and so I will come in and do modify wall panels, and let's just take a look at these same walls in the case of masonry, and I will set this to be applied to all of them. And of course, if we're going to do masonry, we need to significantly cut back on the seismic load, because they're not going to be able to handle 800 kips of seismic. I'm going to drop that down to about 100 kips and go back to the wall design rules. So under the wall design rules, we set these up as concrete wall design rules, but in this case, I want them to apply to masonry walls. So for that, I'm just going to go to this masonry wall tab. And here I can set that maybe I want the exterior walls to be 10-inch blocks and the interior to be 12-inch blocks. We can choose whether it's partially, fully, or ungrouted. We can say whether it's a reinforced or unreinforced wall. And we can even determine the wall area method, whether we have the NCMA tables or the Reinforced Masonry Engineering Handbook methodology. So a lot of this just comes into how you prefer to do your masonry design. Now, we also have masonry in and masonry out, and this controls the in-plane and out-of-plane design of the walls. So under masonry in, maybe for my exterior walls, we could set these guys up to be number 6s, and we'll set them to number 6s for the interior as well. And to set for out-of-plane, I want to use number 6s all around, but maybe for the interior wall, I want to put the bars at each face rather than centered. You can see a lot of other aspects relating to your mortar type and your cement type as well. So you can control all of that. And then coming out here, we can set the interior wall to have that interior wall design rule. And what's going to happen is now this wall will get designed differently from this wall. And so with those design rules, you can really narrow in on exactly what you want to accomplish between them. So now I'm just going to click on this wall, and we can take a look. Here's the masonry results. You'll note that in masonry, we also, if you double-click on the wall, show you the necessary rebar. And so here we can see in this one, there's just a single region, R1. Over here on this wall, we've got, similarly, regions R1, R2, and R3. And so taking a look at the detail report for R1, for example, on this wall, here's my shear and moment diagram and my code checks. And it's a little bit different from concrete, because the design of masonry, of course, is being done according to ASD as opposed to LRFD. If I wanted to get a strength design of masonry, though, I could just come in here under the global parameters and set that to be a strength design instead. And so coming back and solving that same wall again, we can come back, we get our axial, our bending, our shear, and this is presented in both the detail report, and you can get tabulated here in the spreadsheets as well. Now for this last model here, I'm just going to open up an existing model that I've created just to show you the wood walls. And in this case, what I've created is just a very basic structure here. And what I wanted to point out about this structure is that in wood walls, the stiffness is a little bit different from the stiffness of concrete and masonry, in that the stiffness laterally of your wood walls depends on the sheathing that you have applied to those walls. And so what we have to do is we have to perform an iterative process in order to come up with a design for your wood wall. And so when I solve this model here, what I've got going on is I've got a 15 kip seismic load and these two walls running in the same direction, which are both going to be picking some of it up. But if I take a look at my design rules that I've set, and that's part of that wall design rules spreadsheet, under the wood wall fasteners, I've set one up to be a single-sided sheathing, where I set double-sided panel to no, and the other one with both sides. So I said double-sided panel to yes. And so solving this model here, the program is going to come up with a design of single-sided sheathing here for this wall. And for this one, it came up with a 15/32 with 10D nails at 2 inches on center. For the both side sheathing, here you can see it's recommending two 15/32 with 8D nails at 4 inches on center. So a totally different design for these two walls. But what's going to happen as a result is because this has sheathing on both sides versus this one having sheathing on a single side, I have a perfectly symmetric structure with a symmetric load. But if I compare the results, the reactions between these, taking a look at wall panel 1 versus 2, you can see the wall panels end up taking a very different amount of load in the x direction, and that's just because their relative stiffnesses are different in this case. Now, we can also take a look in the terms of the relative stiffnesses down here at the deflection results. And one thing that you know, one way that you know that you're getting a good analysis of your wood walls is if your FEA deflection comes close to the hand calc method of deflection. If I come into this wall here and take a look, according to the hand calc methods in the NDS book, they say that for a wall such as this, that my total deflection should consist of a portion due to hold down elongation, a shear component, and a flexure component. And if I add those up, the hand calc method says we should get about 0.223 inches of deflection. And then the program by FEA is coming up with a deflection of 0.221. So we know for that wall that's good, and here 0.241 versus 0.236. This is just proof right here to make you comfortable with the knowledge that the stiffness of the wall, which of course stiffness can be attributed to deflection, is going to be very accurate relative to what your hand calc methods would be. So you can use this to basically prove, if you needed to, that your calculations are accurate within the program. Now, I know we tried to cover a lot of topics here, but I think we really hit on a lot of the more general wall topics. And so at this point here, I just would like to point out that if you have further questions on any of this, of course, we have an excellent help file available for the program and a lot of other resources on our website, and of course, technical support.